Our global energy infrastructure is approaching a physical wall. As we attempt to power utility-scale quantum computing and entire fleets of electric vehicles, we are reaching the theoretical maximums of classical chemical storage. Classical electrochemistry is governed by extensive scaling laws. In these systems, properties like mass and volume scale proportionally with the size of the battery. If you double the energy capacity, you must double the physical footprint. Because traditional batteries rely on the physical diffusion of ions across an electrolyte medium, a larger physical volume creates a longer path for those ions to travel. This makes charging a strictly extensive process. A battery with twice the capacity requires twice the time to charge. Engineers have pushed lithium-ion and solid-state architectures to their practical efficiency limits. But because they are bound by these linear thermodynamic laws, iterative improvements cannot solve the exponential energy demands of the near future. Addressing this requires a move beyond ionic diffusion and into the second quantum revolution. Researchers are now actively manipulating individual quantum states, using coherent light-matter coupling to directly store and transfer work at the molecular level. This relies on bipartite entanglement. When a localized group of molecules is exposed to a shared electromagnetic field, they do not absorb energy as isolated independent entities. They become highly correlated, functioning together as a single macroscopic architecture. This side-by-side visualization shows the difference in charging dynamics. On the left is the linear classical model, where charge time scales directly with capacity. On the right is the behavior of an entangled quantum battery, governed by the 1/√n charging rule, where n represents the number of active molecular storage units. As n increases, the curve collapses. If you double the physical capacity of this quantum battery, moving from n equals 1 to n equals 2, the time required to reach a full charge is reduced to approximately 71% of its original duration. By converting quantum correlations directly into extractable energy, physical scale is no longer a thermodynamic liability. At the industrial limit, the system charges faster as its capacity increases. The theoretical foundation for this collective behavior was established in 1954 with the decay model. It initially described superradiance, a phenomenon where a group of excited atomic emitters releases its stored energy collectively rather than sequentially. Because these emitters act in unison, their output creates constructive interference. The result is an intense energy burst where the peak emission power scales in proportion to n squared. The time reversal symmetry of quantum mechanics dictates that any system exhibiting enhanced emission rates must possess a correspondingly enhanced absorption rate. This symmetry is what allows for superabsorption. To trigger this absorption, engineers place a dense ensemble of two-level quantum systems inside a resonant optical cavity. When exposed to an incoming laser pulse, the entire molecular group absorbs the photons collectively in mere femtoseconds. But this creates an engineering paradox. The exact same collective coherence that enables ultrafast absorption dictates that the system should immediately undergo superemission. It absorbs the energy in femtoseconds, but re-radiates it before it can be used. In a closed, idealized environment, a quantum battery would oscillate indefinitely between charged and discharged states. Without a physical way to trap the energy, pure quantum coherence is useless for actual work. To bridge the gap between a fleeting physics anomaly and a functional battery, engineers must break the symmetry of the light-matter interaction. They achieve this by utilizing environmental noise and continuous dephasing. This Jablonski diagram illustrates the process. During the initial charging phase, external laser energy is rapidly absorbed, populating highly radiant, delocalized states known as bright modes. Environmental dephasing then triggers an optical ratchet mechanism. The noise drives non-radiative transitions, forcing the energy to cascade out of the unstable bright modes and into a dense manifold of inactive dark excitonic states. Because these dark states possess transition dipole moments that do not couple to the surrounding cavity vacuum, they cannot spontaneously emit photons. The energy is effectively trapped until electrical extraction is initiated. By mimicking the light-harvesting complexes found in natural photosynthesis, engineers transformed environmental decoherence into a trapping mechanism for stable energy storage. In 2026, a collaborative team from CSIRO, RMIT, and the University of Melbourne transitioned this technology from abstract mathematical modeling to applied electrical engineering. They constructed the world's first fully functional charge-store-discharge quantum battery. The device operates at room temperature, built around a multi-layered Fabry-Perot microcavity enclosed by highly reflective silver mirrors. The internal absorber matrix utilizes copper phthalocyanine dye. These molecules are packed at densities approaching 100 trillion per device, functioning as the required two-level quantum system. The definitive breakthrough was the integration of a fullerene, or C60, acceptor layer directly adjacent to the active quantum material. The energy gradient at this donor-acceptor interface drives immediate charge separation. This translates the trapped quantum states into a measurable, macroscopic electrical current. Researchers used transient reflection spectroscopy to confirm that the device retained its stored energy for nanoseconds to microseconds, 6 orders of magnitude longer than the femtosecond timeframe required to charge it. While the output this laboratory prototype is currently measured in microwatts, it proves that macroscopic work can be physically extracted from superabsorption at room temperature. The most immediate commercial application for this technology is resolving the cryogenic bottleneck currently limiting the scaling of utility-grade quantum computers. Superconducting processors require massive, energy-intensive dilution refrigerators to maintain operating temperatures approaching absolute zero. Current architectures rely on thick coaxial microwave drivelines to connect room-temperature electronics to the qubits. These wires inadvertently act as thermal conduits, leaking heat into the ultra-cold processor. A recent study in Physical Review X proposes replacing these external drivelines with a microscopic pre-charged bosonic quantum battery integrated directly onto the quantum processor chip. Because the internal battery and the computational qubits share an entangled connection, energy is transferred to a qubit and then returned to the battery during logic operations. This allows the system to recycle energy internally, eliminating the need for external drive pulses. By removing these thermal loads, internal quantum batteries enable a 4-fold increase in qubit density within the same cryogenic volume, directly accelerating the path to fault-tolerant computing. Despite these breakthroughs, current organic microcavities store only billion electron volts, an infinitesimal fraction of the gigajoules required for electric vehicles or grid storage. To reach that scale, research is pivoting toward hybrid designs. This strategy acknowledges that while quantum systems are unparalleled for rapid energy capture, classical chemical and capacitive systems remain superior for stable, long-term retention. The goal is to strictly bifurcate the charging mechanism from the storage mechanism. In this model, the optical microcavity acts as an ultra-high-speed funnel. It captures light almost instantaneously via superabsorption and then rapidly transfers that energy into a stable, macroscopic chemical bond or classical storage block. By combining the collective capture of quantum physics with the stability of classical storage, hybrid architectures lay the groundwork for wirelessly charged, macro-scale power grids. The current state of quantum energy storage is often compared to the 1903 Wright brothers' flight at Kitty Hawk. That first flight lasted only 12 seconds. While it was commercially useless, it definitively validated the physics of aerodynamic lift. Similarly, the microsecond retention achieved by 2026 prototypes validates the thermodynamics of collective quantum energy. The 1/√n scaling rule and full-cycle energy transfer have moved beyond academic modeling to become laboratory realities. With the underlying physics confirmed, the realization of macro-level, wirelessly charged energy systems is now a matter of strategic industrial execution.